Hello, friends. Alright, so we're going to be talking about z-scores. I try to make this as quick as possible. Alright, so z-scores is the number of standard deviations and that's omega. A value is from the mean, okay? And that is mu, okay? Remember my cow shirt, all right? On the normal distribution curve. So we kind of talked about this when I first talked about the empirical rule and us putting things on a bell curve. This is actually what it's called. It's called a z-score. So these first questions are, what is the z-score of the value indicated on the curve? So meaning the value indicated is this right here. Woohoo! All right. So it's saying, all right, well, what is it? And it's looking like this is off. I guess Google Docs didn't like us when we printed this. This arrow is supposed to be right here. I promise. Ignore the black one. Okay, so this would be the z-score is 1 because it's exactly 1. All right. Same thing happened over here. The arrows are off. Okay, so that would be a z-score of -2 because it's 2 standard deviations away from the mean. Okay, this is 1 standard deviation away from the mean. Now this one's on the left. Okay, so that's why it's negative. All right, now this one is actually where it's supposed to be. So this is a awkward amount away from one of those whole numbers. So that's what z-scores are for. You know, it helps us figure out what is that awkward distance. Okay. So rather than estimating, and I know you guys would love to estimate, but rather than estimating, we are given a formula to help us find the precise z-score. Okay. So you know, we have all these little scary symbols. So Z means z-score. X means raw score. So that's like the given item. So that's that arrow that we were looking at on these examples. Mu is the mean, still always the mean. And then omega is the standard deviation. Okay. Again, most of these items will be given to you, so it's not like where you're not having to do a lot. All right, example 1. The mean score on the SAT is 1,500 with a standard deviation of 240. The mean score on the ACT has a mean score of 21 with a standard deviation of 6. If Bobby had a raw score of 1,740 on the SAT and Kathy had a raw score of 30 on the ACT, who did better on the exam? So this is how we can use z-scores to help us figure out, okay, comparatively, these tests have very different meanings. But if we look at the z-scores, we can see, oh, did they do better than each other or worse? Okay, so let's figure out z-score for Bobby and Kathy. So the z-score for Bobby, not body, Bobby, okay, we're going to use this formula up top. So the raw score, given value. Okay, so the raw score, hey, that's so nice, it gives it to us. This could be 1,740. Okay, minus the mean. Here, right there. Mean score on the SAT is 1,500. Divided by omega, standard deviation. Standard deviation of 240. Okay, so at this point, you would just take it and type it into a calculator. So let me grab my Desmos fun business real quick. All right, I have my Desmos. So we have 1,740 minus 1,500. This is the one thing about having a mobile phone on the Desmos. Alright, so when I type it all in, I get 1. Isn't that cool? 1. So Bobby's z-score is 1. So he was 1 away from the mean. So if we were to look at like this, just ignore that. He would be right here. Okay, he is somewhere right here. So he's above the average. He's pretty good. All right, So let's look at Kathy. How did Kathy do? Is she smart? So we're going to do the exact same thing. So Z of Kathy is equal to her raw score of 30 minus the mean on the SAT. So the mean score on the SAT is 21, and it has a standard deviation of 6. So again, we're going to do the exact same thing. So I'm going to pull up my handy dandy Desmos. So we have 30 minus 21, all divided by 6. We get 1.5. Well, she has a bigger Z-score. So again, interpreting this, ignoring that. So Bobby landed here, but Kathy landed here. Okay, so Kathy did better test-wise. Okay, so because she was further away from the mean in a positive sense. Okay, so Kathy, she's smart. So now we have a different type of question. It says, Jim has a Z-score of negative 1.25 on the SAT, so he did lower than the mean. What was his raw score? Okay, so we want to just figure out what he scored. So we're going to use the same exact equation, but we're going to solve for the raw score. So if this, makes you scared, it's always helpful to write out what each variable is. All right, so Z was negative 1.25. X, that's the raw score. We don't know that. That's our question mark. Mu is the mean. So we're still using the same mean from previously. And we're doing SAT, so that is 1500. Omega is the standard deviation. So right there, standard deviation is 240. So now we can set it up. Negative 1.25 equals X minus 1500 all over 240. Okay? And you can get Desmos to solve this. Again, you could just type that whole thing in the Desmos, or you could solve it by hand. Negative 1.25 equals X minus 1500. 240. Okay? So you have to zoom out and look for the little intersection, and it's right there. 1200. So we get X equals 1200. So Jim's score was 1200. That's near my SAT score. Now it makes me feel a little stupid. Alright, let's keep going. The weight of an average 3-month-old child is 12.5 pounds, not mine, with a standard deviation of 1.5 pounds. Benjamin is a healthy 3-month-old that weighs 13.9 pounds. Determine the Z-score for Benjamin's weight at 3 months. Okay? So again, average 12.5 pounds, standard deviation 1.5 pounds, and Benjamin is 13.9 pounds. So I'm going to write all that down. So we got Z, we got X, we got mu, we got omega. Z, we do not know. That's what we want to know. The raw data, raw score, is going to be 13.9 because that's how much Benjamin weighs. Okay? Mu is the mean. The average 3-month-old was 12.5 pounds, and omega is 1.5. So I'm going to set up my equation. Alright, and then I simply just type that all into Desimosa. Okay, so we have 13.9 minus 12.5, all divided by 1.5. And we get this, okay? It is going to be a decimal, and that is a-okay, friends. Okay, we're just going to do 2 decimal places. 2 or 3 is fine, whatever you want. So we're going to do 0.93. So that is his Z-score. Okay, so then this next thing is determine what the Z-score means in a sentence. So all this means is that Benjamin, okay, is 0.93 standard deviations above the mean. Okay, so the cool thing about this sentence is that it's not really going to change regardless of the context. So you're always going to have your value, that your z-score here, and it's always going to be standard deviations. And then this word is either going to be above or below. It'll be below if your z-score is negative. Okay, so it doesn't really change. All right, so we have this next question. It says the weight of an average 6-month-old is 17.25 pounds with a standard deviation of 2 pounds. If Benjamin has the same z-score at 6 months as he did at 3 months, determine how much 6-month-old Benjamin weighs. Okay, so there you go. Average, standard deviation, same z-score. Okay, we want to know how much he weighs in the end. So again, if you get confused, just write out all the variables and what they would stand for. So average is 17.25, so that means the mean, omega, is 17.25. My child does not weigh that at all. She's like 14. Standard deviation is 2, so that means omega is 2. And it says, what if he had the same z-score? Well, his z-score was that 0.093. Okay, and we want to find out what the raw is. Okay, so we're going to set this up. So 0.93 equals x minus 17.25 over 2. And you can do the exact same thing that we did before, where you have Desmos, just solve the equation. So 0.93 equals x minus 17.25 all divided by 2. So we got to zoom out, look for that intersection. Sometimes it appears. 19.11. Okay? Hey, that's pretty nice. And that's it. Okay? So it would be about 19.11 pounds. Alright. Let's move on. So, what I want us to do here, I want you guys to try this one on your own. So pull out Desmos, whatever way you want to pull it out, and answer at least, all the questions, okay? And then I will show all the work and I'll explain it once I'm done, okay? So pause and do these 3 questions. Alright, so here is all the work. So again, your question tells you exactly that the mean for women is 64, standard deviation is 2.7, okay? And then again, for the men, mean is 69.3, standard deviation is 2.8. So all you're doing for these first 2, you're told that John is 81, June is 74. You're finding those 2 standard z-scores and seeing who has a larger z-score, in this case John. For letter B, if you have a z-score of 1.5, you have to solve for the raw score, so 68.05. And then same exact setup for letter C, it's just you're going to compare your solutions. So the woman would be 67.24 inches if they have a z-score of 1.2, and the man would be 67.9 inches if they have a negative 0.5 z-score. Okay, so the man would be taller. All right. So go ahead and try these ones, and I'll show the solutions in a minute. So pause. So I just want to do a small check-in after example 6. So if you notice, I've been writing out all of the information that I know I have from the problem and then putting it into my formula. So again, we were given a raw score of 2, given the mean and given the standard deviation, but we want the raw score. Okay, so X is my question mark. Same thing here. We're given a raw score of 12.06. We're given the z-score of negative 1.6. We're given the standard deviation, but we want to know the mean. Same thing here. We are given the raw, we are given the mean, we are given the standard deviation. We just don't have a z, so we can solve. All right. So pause here. I'll put up the answers, and then we'll be done. So here are the last 2. Again, they're very similar to the other ones that we've been working on and all that jazz. All right, do your homework. Have a wonderful day. Love you.